Uh, Today we're going to be continuing with chapter 16. Try to finish that. Maybe look at a little bit of homework. Reminder that test was due. So got most of them in. So for those still left, turn them in when you can. I'll post a video crib working it out. There's a few common mistakes. We'll talk about that in the video eventually. Meantime, we'll continue with our current thing, which is chapter 16. And I think there's going to be a maintenance on Achieve Sunday, March 7th. So if you're trying to get into it on Sunday in the eve at midnight to 7 a.m. time frame, you might have a little bit of trouble. But okay. Oh, for God's sake. Okay. So one thing we should talk about is the effect of pH active salts. The idea, like, some things you obviously know this is acidic, or you obviously know it's basic. If I put acetic acid in water, we know it's going to form some acid. We know we put some ammonia in water, it's going to form some base, because those are our standard weak acids, weak bases. But sometimes you'll put a salt in water and it will form some acid or some base. And we don't always have a good clue on that. So we're going to go in and kind of look at that. What makes a salt pH active? Sometimes salts lacking acidic proton or lacking an obvious hydroxyl group will affect the pH. The whole idea here, as long as they are a conjugate pair for a weak acid or a weak base, they can do this effect. The most obvious one would be ammonium. If I have any sort of ammonium salt is the conjugate acid of ammonia, which is a weak base. If I put ammonium in water, it's going to establish an equilibrium where it breaks from ammonium back into ammonia and produces some acid. Now, some conjugate bases of weak acids will do the same thing, like hypochlorite, sodium hypochlorite. Perchloric acid is a strong acid, but hypochlorous acid is a weak acid. So in the case of hypochlorite, establish an equilibrium that reforms the acid and makes hydroxide. Some of those are going to be kind of obvious. Some of them are going to be a little bit less obvious, especially when we talk about Lewis acids. McMillan's giving me trouble. Lewis acids. So cations such as iron, aluminum, chromium, copper, zinc, cadmium will form what's called a hydrate in water. That, truthfully, it's never just iron 3+ floating around by itself, but it's iron solvated with 6 molecules of water, or copper solvated with 6 molecules of water, or zinc solvated by 6 molecules of water. And in this solvation process, this water can act acidic, donating a proton to form a stronger, what it's called, a ligand, this binding structure that binds to the iron. So iron hexaaqua becomes iron pentaaqua hydroxide, or iron pentaaqua hydroxyl. and donating a proton. This can happen in many of these strongly charged transition metals. Come on. In general, there's 4 different possible situations we can have when we put a salt in water. Really, this doesn't explain which one it is, but there's 4 possibilities. 1, it's a straight up neutral salt. Just a salt. Salty as salt can be, it's not going to act special. In this case, both cations and anions are conjugate acids and conjugate bases of a strong base and a strong acid. The rule, remember, is if an acid is strong, it 100% dissociates. If a base is strong, it 100% dissociates. So that means the reverse reaction is essentially 0. If the reverse reaction is essentially 0, then it's not going to go backwards. So HCl, for example, is a strong acid. When you mix it with water, it forms H plus and Cl minus. Cl minus is just going to be a salt. It's not going to go backwards. Sodium hydroxide is a strong base. I mix sodium hydroxide with water. It's going to form Na plus and OH minus. It's not going to go backwards. NaCl would be the salt using the Na from NaOH and the Cl from HCl. When I put salt in water, the pH will change 0. It should not change at all because Cl minus is the conjugate base of a strong acid, and Na plus is the conjugate acid of a strong base. Now, there's the 2 obvious pairs, which acidic salt, the cation is either one of the stated metals or the conjugate acid of a weak base. So please note, the cation, it's either the cation is acidic. Yeah, the cation is going to be responsible for whether it's an acid or not. The cation is responsible for whether it's going to be an acid or not. So you look to the cation to figure out, is this going to act acidically? Examples, iron chloride. If I mix iron chloride in water, it's going to form some acid because iron is one of the stated metals. Ammonium nitrate. Ammonium is a conjugate base of a weak acid. Conjugate acid of a weak base. And aluminum is one of the stated metals. Basic salts, the flip side of that coin. So for a basic salt, you look at the anion. The anion, is the anion a conjugate base of a weak acid? That one's a little bit easier. Acetate is the weak base of acetic acid. Here's a tricky one. SO4. SO4, the acid H2SO4 is strong. However, HSO4 is weak. HSO4 is weak. This is from a polyprotic. So this will absorb some protons to reform the HSO4. And of course, LiF. F from F1 minus from hydrofluoric acid. The one that's a little bit harder is the unknown pH salt, where both cation and anion are pH active. If you were to ever get this case, and I would rarely, if ever, throw this case at you, you would have to look at the Ka and Kb and determine which one is stronger. Determine which is more effective, the Ka or the Kb. So determine the Ka of a weak base or the Ka of a weak acid. You can remember that relationship. But just note, if you look at the Ka of one and the Kb of the other, the bigger one wins. The one that's closer to one wins. So how to do this in practice? If you were asked, determine the pH of the salt solution, or determine whether this would be pH active salt, how would you go about doing this? So you look at the cation anion pair. You split it into cation and anion. You would add hydroxide to the cation into its neutral. Does this look like one of the 8 strong bases? If you add hydroxide to this, does it look like one of the 8 strong bases? If not, it's probably pH active. For the anion, add a proton to the anion. Just one. Don't add more than one, just add one. Does it look like one of the 9 strong acids? No, and it must be pH active base. If the answer to both were no, we have to look at the size of the Ka of the conjugate acid, size of the Kb of the conjugate base. If one is bigger, then it's if Ka is bigger, then it's acid. If Kb is bigger, then it's base. Okay. Let's look at this in practice. Easiest way to do this, pull up the doc cam. You can write these out. Nickel chloride, cesium iodide, CH3, 3NH. There are 3 of those. Phosphate. And barium iodide. Hypoiodide. Okay. Go to the doc. So all these cases, we're going to split these into cation-anion pairs. Remember, whatever one of our 9 strong acids. We have HCl, HBr, HI, HNO3, H2SO4, HClO4, ClO3, HBrO4, and HIO4. Let's see. Look at how many bases did I say there was? Oh. One of 8 strong bases. Okay. Back to the doc cam. All right. 8 strong bases are all of your group 1, LiOH, KOH, RBOH, CSOH, then I think trying to remember if there's what the other one is. I think calcium hydroxide can be considered a strong base, but definitely strontium hydroxide and barium hydroxide. I'm missing one somewhere. It's 7. MgOH2 is not one. LiOH2 is not one. Oh, Li, forgot Na. There we go. NaOH. 1, 2, 3, 4, 5, 6, 7, 8. The strong bases, all of group 1 and group 2, except for the first 2, are strong bases. Now, remember the acid, the cation will determine if it's acidic. The anion will determine if it's basic. Looking at that, Ni 2 plus, Cl 1 minus. There's 2 of them. Now, if I add hydroxide to this guy, into its neutral, NiOH 2, and H, add 1 H to my Cl, HCl. This guy is a strong acid. This guy is not a strong base. Nickel is one of our metals. Nickel is one of our metals. So in this case, Cl minus plus water will not do this reaction. It will be a teeny tiny way forward, a lot of the way back to HCl and OH minus. So this is largely reactant favored. So Cl minus is a pH inactive anion. Nickel dihydroxide is not. So nickel 2 plus 2 waters is going to somewhat favor forming the nickel dihydroxide or something like that. So what does this mean? The nickel chloride would be an acid. Nickel chloride would be an acid because the cation is not a strong base, does not belong to a strong base. Let's look at cesium iodide. Cesium plus 1 and iodide minus 1. Cesium, if I put in a OH, cesium hydroxide, put H with I, we see here cesium hydroxide, one of our strong bases. HI, one of our strong acids. These are the conjugate acid of the strong base, and that's the conjugate base of our strong acid. This guy would be neutral. Cesium iodide would have no effect. Moving down, CH, this is a weird compound, but NH plus. Okay, no, sorry, I drew it wrong. Doesn't really matter, really. And this is trimethylammonium. Trimethylammonium. It is the version of ammonium with, instead of hydrogens, it has carbon groups. Trimethyl, the conjugate base to this acid is trimethylamine. Just like ammonia is trimethylamine, and this goes to trimethylammonium upon protonation. Now, the other guy was PO4 3 minus. If I put a hydroxide here, CH3 NHOH, does that look like any of our strong bases? No. If I put a proton here to HPO4 2 minus, does that look like any of our strong acids? No. So the question is this pH active? Yes. Which one is more pH active? That requires us to look at the difference in the Ka and the Kb of these two guys. So you would have to find out the Ka of this guy, or sorry, the Kb of this guy and turn it into Ka, and the Ka of this guy and turn it into Kb, and look at the size. I really don't care right now which one's stronger, but this is going to be active, more info needed. If I gave you a problem like this on a test, it'd be more info needed. Because without knowing the Ka and the Kb, and you're never going to need to memorize any of these numbers, Ka and Kb, they will be given if you actually need them. This would be a more info needed type situation. The last one, barium iodide, barium 2 plus, hypoiodide 1 minus. You put hydroxides until you got this, BaOH2. That's a strong base. Iodide, HIO. There's a HIO4, but HIO is not HIO4. So this is a weak acid. This is the conjugate base of a weak acid. So in the presence of water, this is going to go to HIO and hydroxide. So since this is a strong base, this is not an acid. Not an acid. But because this is a weak acid, the conjugate base means this is going to be basic. So the last one will be basic. What you have to do is you split it into the cation and anion pair. Then you compare your strong, whether this is going to be related to a strong acid or strong base. And if it's related to a strong base, it's not acidic. If it's related to a strong acid, it's not basic. If it's related to neither, then it really depends. You have to look at the stuff. So acid, just a salt, more info needed, and definitely a base. But you can determine how this is going to interact based on looking at just those two things, the cation and the anion. Now, there are several factors that will actually control the strength of our acids. What makes HSO4 strong? What makes HNO3 strong? What makes H3PO4 weak? What makes HCl strong but HF weak, and HBr strong and HI strong? What makes H2S weak? So there's three things. Some of them are easy to see, some of them a little bit harder to see. The first thing has to do with bond electronegativity. How well does the anion pull the electron density away from the hydrogen? The more electronegative the atom, the easier this is. The easier it is for that proton to be lost. If that electrons from the hydrogen have been already essentially pulled away, then it's going to be very easy for that naked nucleus, that single proton, to float away into solution, to get stick with a water molecule. Bond electronegativity is one thing. Now the next one's a little bit harder, and it explains why F minus. F minus, which is the most electronegative atom, why that's a weak acid, and HCl is not. And this has to do with bond strength. It doesn't matter how much those electrons are pulled away if the bond is too strong. This one's a little bit harder. You can't just look at a table, look at a chart, and kind of figure this out. If the bond is too strong, then ionization becomes incomplete. But that's what makes HF weak, but HCl strong. HCl has a weaker bond, but is still a strong electronegativity, which allows that to break. Now, here's the thing that makes this, that we can look at. Stability of the conjugate base. Some of this you have to go back to our Lewis structures. So we still need to remember some of that stuff. But how well can the ion hold the charge? How well can we distribute this charge? This is another thing. Cl minus is better at than F minus. F minus is a small atom, and when it accepts a charge, it becomes highly charged. It only has like 9 protons, I think. Remember, right? And so to add another one, 9 protons, 9 electrons, to add another one to get to 10, it adds a big chunk. Chlorine would be 19, if I'm not mistaken. Oh, no, not 19, but 17. And to add another electron is a lot easier. 17 to 18. It's a smaller jump. Same thing with bromine. Bromine's actually even easier. It is larger molecule. There's a lot more electrons. I think that's one's closer to like, oh God, another, what, 19 plus 17, 20, like 36, 35, something like that. No, 36. I think it's 37. Sound like 37. It's getting bigger, and so 37 to 38, much smaller jump. And the same thing going down. However, this also will explain why a lot of these oxyanions are strong acids. The more oxygens these guys have, the more resonance structures they will have. When you have a resonance structure, you can spread out this charge equally throughout the whole compound. The better you can spread out this charge, the better you can stabilize this compound. The more resonance structures you have, the more stable this anion will be, because instead of a full negative being on one atom, you have a negative spread out on 2 atoms or 3 atoms or 4 atoms, thus stabilizing the structure. So we have a couple different charts in here. Just looking at some of these guys. Okay, here we have acetic acid with its relative Ka. If I put a chloride on here, the chloride does what's called an inductive effect, where it's going to draw electron density away from the oxygen and the 2 oxygens. So when we lose this proton, you can better stabilize that negative charge. And so you'll notice the Ka gets larger. If I put a second chlorine, the Ka is getting larger still. If I put a third chlorine, the Ka gets larger still, so that it becomes more acidic the more of the electron withdrawing groups we have. This looks at our, I think maybe the the bond strength versus trying to read that such small letters. We look at here, we have increasing stability and increasing size. We can look at how the different ions have a different pH. We look at bond energy. How the bond energy essentially increasing atomic size, we have increasing pH. With increasing bond energy, we have decreasing pH. That just little tables showing how these are relating to the actual pHs of some of these strong acids and weak acids. Take a good look at that at your leisure. Right? I realize on the screen it's a little hard to see. I need to zoom in. It's also in the notes. Right now it's so hard for me to read the exact numbers to give them to you. But also oxyacids and organic acids. Now, as I said, the oxyanions, we have a lot of strong ones and maybe a lot of weak ones that we wouldn't see otherwise because of the stabilization. One, they will depend on the electronegativity of the center atom to help, but also the number of oxygens around the center will be another effect. The more electronegative and the more oxygens, the stronger the acid. Now, looking at HClO4. HClO4, if you put the Lewis structure of that, you would look something like this. And if you go to the conjugate base, you have that O minus. If we draw the resonance structures, you could move the double bond there, put the charge there. Move the double bond there, put the charge here. Move the double bond there, put the charge here. You could have 4 different resonance structures. And so this negative charge is spread out among 4 different oxygens. If I do HClO3, that chlorine suddenly has a lone pair. And now when we lose the H, we have 3 resonance structures. Now, HClO3 is still a strong acid, but it's a weaker acid than HClO4 is. You can imagine if we had HClO2, which would be chlorous acid. It is a weak acid. When it dissociates, it only has 2 resonance structures. And HClO would have only the one structure you could draw because it'd just be O minus Cl. Even organic acids like acetic acid, we can see these resonance structures. This is going to stabilize us. Carbonic acid or acetic acid is a weak acid. However, it is an acid. If we compare this to ethanol, you could see what effect this carboxylic acid has. I'm going to pull this up. Now, ethanol can be an acid in a strong enough base. So CH3, CH2, OH. If I put this in a really, really strong base, like we'll say O2 minus, oxide, straight up oxide, then yes, this will act as an acid and donate a proton. CH2O minus, and then would have OH minus as the product. However, in standard base, if I put hydroxide here, it's going to be no reaction. As opposed to our CH3, C double bond O, OH. We're going to see the reaction. It goes to water and our CH3, C double bond O, O minus. That the fact of this resonance structure where this double bond can swap from here to here, taking these lone pairs, is going to allow this to be stabilized anion. There's no resonance structure we could draw. There's no resonance structure we can draw because carbon is obeying the octet rule. We can't rearrange any electrons without breaking the octet rule. This guy, I can swing these electron pairs down, swing this lone pair up, and essentially put the negative charge here, and we still have the octet rules obeyed. So our resonance structure says this guy is stabilized and thus can act as an acid. This guy is not stabilized. It takes a really strong base to make it act as an acid. Can it act as an acid? Yes. In organic chemistry, you will learn, if you have organic chemistry, that you can make ethanol into an acid, but it takes a certain type of situation. Some very strong acids, very strong bases, and you'll learn, oh, this is an acidic group, this is a basic group, and why this is acidic and basic, and it all comes back to this stuff right here. So while you may think, oh, we're not going to really deal, we will see some of this stuff again in organic chemistry. So please don't just blank out your mind completely for this stuff. We will see it again. Okay. No, need to. The last concept we'll talk about is Lewis acids and Lewis bases. A Lewis acid and Lewis base is the broadest definition of an acid and a base. This includes all Arrhenius acids and bases, all Bronsted-Lowry acids and bases, but it adds a whole new group of compounds to the acid-base category. Basically, Lewis acids and bases are named because they're based on the donation of lone pairs of electrons that are typically observed within the Lewis structure. Figured out by what? The scientist Lewis. The last name Lewis. I'm trying to remember his first name. Doesn't really matter right now. But the idea here is, by definition, a Lewis acid is an electron pair acceptor. By definition, a Lewis acid is electron deficient. Something that has less electrons than it wants and can accept electrons. In organic chemistry, you'll be dealing with a lot of Lewis acids and bases. Typically in organic chemistry, you'll call these things electrophiles, things that are electron hungry, electron lovers, things that will attack negative centers because the lone pairs will be attracted to this and they will be attracted to them. H plus is the best concept of a Lewis acid. H plus has no electrons. H plus would like 2 electrons to fill its doublet, the s orbital. So H plus is the standard Lewis acid. However, things like boron can be a Lewis acid. Boron, remember from in General Chemistry 1, has 3 electrons. It can typically only make 3 bonds. That would give it 6 out of the possible 8 electrons. It is one of the atoms that typically does not achieve an octet because it doesn't have electrons to do it. This makes this guy a Lewis acid, guy who needs electrons to give it an octet and just doesn't have it. It's electron deficient. Many transition metals are Lewis acids. When we talked about those pH active metals, those were because they were positively charged. They're missing the electrons they need to achieve their special transition metal charge. So they became Lewis acids. Now, Lewis bases are electron pair donors. Electron pair donors. And they typically will have a large amount of lone pairs that they can donate. OH minus, typical Lewis base. If you draw the Lewis structure of OH minus, you should have 3 lone pairs on the oxygen. Those lone pairs can donate electron density to a proton to make Lewis acid Lewis base. But F minus is also a Lewis base. F minus would have 4 sets of lone pairs. Any base we had before is now a Lewis base. The big thing is that we've now added a whole bunch of metals and electron deficient atoms that can now act as Lewis acids. So we don't have to deal with protons and hydroxides anymore. We can look at it as just terms of electrons going in, electrons going out. As I said, BH3 is a common one. Some transition metals are also Lewis acids. Now we no longer have to deal with hydroxide. In this case, Lewis acid and Lewis base can form what we call a Lewis adduct, where that's held together by a coordinate covalent bond of shared electrons. So boron has not enough valence electrons to give it an octet. Ammonia has 2 valence electrons that are in a lone pair, 3 that are in a bond. This lone pair can donate to the boron and make this guy have a formal charge of +1, a formal charge of -1, and ammonia to have a formal charge of +1 to make this new Lewis adduct compound that everything has an octet. We'll see a lot of these in different catalysts when we look at organic chemistry. There'll be plenty of Lewis acid catalysts that make some of the chemistry work. Like the Grignard reagent is a Lewis acid catalyst. You mix like magnesium chloride into this thing, and they essentially make a catalyst that can donate a alkyl anion to certain groups. Or you might use iron trichloride as part of a Lewis acid catalyst to add a halogen onto a benzene ring. There's lots of Lewis acid catalysts that will come up in the future. Maybe not so much right now, right here, but in the future, they will still be coming up. Whether you recognize them as Lewis acid catalysts, that's up to you, but they are there. They will not go away. But that is this chapter. This chapter was to introduce the basics of Lewis acids, Lewis bases, and how do we treat all of our basic math here. We took it through equilibrium. We took it through equilibrium. We dealt with pH, and we did learn the Ka, the ice table, and all that stuff. This up. This is not due for a while. This is not due till March 9th. So we have a little bit of time before chapter 16 is due. Yeah, we have, I'll just do one of these, part of these. Determine the OH minus pH and POH of a H plus concentration of 6.4 times 10 to the negative what? I'd like to say 12? Negative 12. 6.4 times 10 to the negative 12. 6.4 times 10 to the negative 12. And they want to know everything about that. All the interrelated goodness. In itself, not too hard. However, there's multiple different ways to go about this. You could go this to pH, to POH, to OH minus. You could go this to pH, to POH, and this to OH minus. Or you could go this to OH minus and then POH. It doesn't matter how you do this. There is this interrelated relationship that can get us all the way back. It doesn't really matter how you go about doing this. I'm going to go the standard one of the ways. I can say that 10 to the negative 14, which is our KW, equals H plus times OH minus. So if I know H plus, I know OH minus. 10 to the negative 14th divided by our 6.4 times 10 to the negative 12. Make sure you got the order of operations in there. Make sure you do it right. 10 root negative 14. Divided by, I'm going to put this in parentheses to make sure I have it right, 6.4 times 10 root negative 12. There should be a biggish number because the other one is a smallish number. 0.00156. 156. So that would be our OH minus concentration. Now to get pH, negative log of H plus gives me pH. So I can just take the negative log of 6.4 times 10 root negative 12. So pH is going to be 11.19. Now it's up to you whether you want to turn this guy into POH or just say 14 minus pH equals POH. Either one works. 14 minus pH equals POH. But I also could have taken the negative log of OH. Either one works. 14 minus 11.19 would be 2.81. Either way works. As I said, there's multiple different ways to find the same thing in here. Okay. So I'm going to go ahead and put in my numbers, at least for the first half, just to show you. Make sure I'm not screwing anything up. 0.00156. 11.19. Of course, I'm going to get part of it wrong because I'm leaving the other part of it blank. Feedback. I left this blank. However, should say I got, yeah. So they got that part right. How many parts? Okay. So they have you do a bunch of them. There's 4 of these problems in here. I did one part of this 4. So I got 25% of the credit. Yes, it's a little bit of busy work, but it's helped to beat in the relationship with H plus, pH, and POH. This next one, they give you an OH minus. And so you would do the inverse thing. You could find the H plus with the OH minus. You could then find POH and pH. This one, they give us a pH of solution. I'll go ahead and do this one just to show how we'd go about doing this. They want it from a pH of 4.84. From pH of 4.84, turn it into all the relevant things. So the first, we're going to go to POH, but we can also then go to H plus and OH minus. So 14 minus 4.84 gives us our pOH of, I could probably do this in my head, but I'm going to just give my brain a break, 9.16. Now, to reverse this situation here, sorry, I forgot to switch back to the document. So 14 minus 4.84 is 9.16. To reverse this situation here, you're going to take, first you make both sides negative, so you have log of H plus equals negative pH, and then you're going to do the inverse log to both sides to get rid of the log. So you have H plus equals log the 10 to the power of negative pH. So H plus would be second power negative 4.84. So we get a number of 0.000014, let's say 145. The other one, you'd have OH minus equals log, the inverse log of negative pOH. So you would have the same thing, inverse log, negative 9.16. You'd get 6.92, 10 to the negative 10th. So we're just showing this relationship. We're just showing these relationships, trying to beat that into us, these basic relationships that will make our lives easier to understand what's all going on. So 0.000145 OH minus is 6.92 times 10 to the negative 10th, and pOH is 9.16. Now, obviously, I'm doing this. I'm not finishing this, so I'm not getting all the credit, but that's fine. I don't feel I need to super busy work. Okay, this one's just recognizing which of these guys is pH neutral, which guys is pH acidic. Remember, high pH means basic, a low pH is acidic. So a high pOH is basic, low pOH is basic. Some of these guys you have to do the negative log of, and 7 is our neutral. pH of this strong acid, that one's pretty straightforward. This one requires you to turn grams into moles into molarity first. But once again, that should not be hard. We just have to remember our general chemistry stuff. Let's see. Ka expression, I'm going to skip that. K of a monoprotic weak acid is this. It's the pH. So, looking at that problem, they don't give, it's not supposed to be anything super hard. We're just reminding us how to do this. 4.2 times 10 to the negative 6 is our Ka. Our HA is 0.2. Now, properly done, we should have a whole ice table and yada, yada, yada. However, most situations, in this case, Ka is small, HA is significantly bigger. This is going to be the very weak acid. We have to do step 1, which is find the H plus. The H plus is going to be the square root of Ka times HA. How did I get that? That comes from the Ka expression, where Ka equals x squared over HA. We got the HA to both sides and the square root of the x. Where that x come from? The x comes from our ice table, where x is equal to both H plus and it's equal to A minus. So don't be confused where this is coming from. This is coming from our ice table, which is coming from our standard Ka expression. I'm just doing a little bit of a shortcut because all of these problems are very, very similar. So the square root of that whole spiel would give us our H plus. So square root 4.2 times 10 root negative 6 times 0.2. H plus is going to be 0.000911, we'll say 7. Notice, much, much smaller than this number. Much, much smaller. And then the second part, since they asked for the pH, is the negative log of H plus. Don't forget to answer the original question, what is the pH? So 3.0, we'll say 4. It technically, if you go for sig figs from what they've shown us, be 3.04. So four. So don't forget to answer the original question. These are two-step problems at least. This one is 3 steps. They give us a Kb, they give us the concentration of a base. You would turn Kb and concentration of a base to OH minus. You would either find H plus or negative log of POH. And no matter what, the last step is you turn it into pH. You have to make sure this is a base. This is not going to give me H plus. You have to find the OH minus and turn that into some sort of acid. So look at 1 or 2. Oh, here's classify these salts as acidic, basic, or neutral. So you would look at this, breaking out potassium carbonate, for example. Potassium, group 1, comes from potassium hydroxide, a strong base. Carbonate would come from HCO3, 1 minus, a bicarbonate, which is a weak acid. A weak acid means it's going to be basic. KCl, K from potassium hydroxide, Cl from HCl, that's going to be neutral. Lithium nitrate, nitric acid, lithium hydroxide, that's going to be neutral. Ammonium perchlorate. Perchlorate comes from perchloric acid, so that's strong acid. Ammonium comes from ammonia, which is basic, so. Then Na, sodium hydroxide, cyanide, the hydrocyanic acid. So we look at cation-anion pairs. Cation-anion pairs. You have to be able to recognize the strong acids and the strong bases to make this go fast. However, I think that start by identifying whether each cation is derived from a stronger acid or weak. Strong or weak, strong acid or weak base or whatever. And it gives you a list of strong acids and bases. So if you don't have it handy, it links to there. So you don't have to have that recorded. You don't have to have a cheat sheet. It gives you, if it's not related to a strong acid or strong base, you can do it. So that one's finding the KB from the KA. Let's see, just keep going. Okay, so this one is a little bit trickier. I'll go ahead and do this one, and this is where we'll finish off, maybe. So the thing of it is they give us the Ka of a weak acid. 4.0 times 10 to the negative 8th. Ka 4.0 times 10 to the negative 8th. They say the salt is a weak base. What is the pH of a solution of the salt? And with a concentration of 0.044 molar. So this is a situation where we are given a base and we're asked and given the Ka for the conjugate acid of that base. And we say, what is the pH of that base? Because here we go, .m. Here we go. The situation we're looking for is ClO minus plus water goes to, reversibly, HClO plus OH minus. To do this, you would say KB equals, that guy's going to be X, that guy's going to be X, that's going to be our base, or A minus. So X squared over A minus. To find our OH minus concentration, it's going to be square root of KB times A minus. Now, here's the problem. We don't have KB. We have Ka. But as long as we have Ka, because of Kw, you can find Kb. Kw equals Ka times Kb. So what does that mean? That means our Kb is equal to 10 to the negative 14th divided by our 4.0 times 10 to the negative 8th. As long as we know our Ka, we also know our Kb because of this magical relationship that's always going to hold true for water. We're always using water in this chapter. So in this case, I'm going to turn this into scientific. 1, 2, 3, 4, 5, 6, 7. 2.5 times 10 to the negative 7th. 2.5 times 10 to the negative 7th. Okay. OH minus concentration, as I said, is the square root of 2.5 E negative 7 times our 0.044. 0.044. Square root of that. We get the OH minus is equal to 1.0, we'll say 5 times 1, 2, 3, 4. A fourth. Negative log of that number, OH minus, will give us our POH. So negative log of that number will give us our POH, 3.98. And then finally, 14 minus our POH will give us our pH. 14 minus 3.98 will give us our pH of 10.02. I'll give us a minute. That went fast. I'm not going to lie, it went fast. What did I do? I looked at, we have a basic solution. So we need a Kb and the concentration of base. From there, we have the same generalized process each time to find the concentration of OH minus. From there, once we found the Kb, it's just my negative log. But you got to remember, base gives us POH. What are they asking for? pH. So the last two steps are almost like autopilot. The first part is understanding what you're dealing with and how to set it up. You have to have Kb. To find Kb, you need Ka. So plug this in. 10.02. That's what it means to be a pH active. You drop just a little bit of this salt in solution. Not very much, 0.044 molar, and it jumps from pH 7 to pH 10. Just by adding a little bit of this salt. I just want to look at what last questions we have remaining. Predict the acidity based on the number of oxygens. We kind of talked about that. Predict the acidity of these various structures. Talk about which one is a Lewis acid, Lewis base. So you've got to look there. Which one of these guys has lone pairs that it's donating? Which of these guys has all of its electrons used up in a bond or no electrons at all? And so the last two ones are dealing with Lewis acids, Lewis bases. So that's what we have left. So this is where we're going to call it for today. On Thursday, we will go ahead and start a little bit of chapter 17, but not too far, just enough that we'll be able to do some of the beginning problems if you so care to look at them. For those of us who have lab this week, we will be doing the kinetics lab. So I got to start making the solutions for that. But it's one where we'll essentially, the kinetic problem, like 7A/B, that's essentially what we'll be doing. We'll be measuring, we'll be setting a set concentration, mixing things together, and trying to figure out the rate. By looking at the rate and how changing the concentration changes the rate, you can look at essentially what are each of the orders, and then what is our equilibrium constant K. Anyway, thank you for your time, and good day.